Okay, so this is the last section of pre-calculus. I know you'll all remember this into Calc 2 because that's really where you're going to use this Calc 2. And today we're talking about geometric sequences. Okay. And the really cool thing about geometric sequences, I mean, this is what they look like, is you're multiplying. So if you have a geometric sequence, so let's say it adds up to something, right? We'll do a couple of terms. So we'll do a plus a times r plus a times r squared plus a times r cubed plus dot dot dot, right? A r fourth. And how you tell if it's a geometric sequence, okay, is you take the ratio, okay? Check for common ratio. So if I take, like, say this two terms, so I say a r cubed divided by a r squared, we end up with, right, all of these cancel except for one of them, we end up with r. But if I take, like, a r to the 7th divided by a r to the 6th, well, again, all of this stuff cancels except for r. So we have a common ratio between each term rather than a common difference between each term. See, if you try to do that with this one, right, if I say ar squared minus ar, well, that's going to be ar, and I'll have r minus 1 here, and that's a difference. But if I try for a different, right, pick any other two, then this is going to be a little bit different. So, like, wait, if I want ar to the 6th minus ar to the 5th, so we still get the pulling ar to the 5 out, we still get this r minus 1. So it kind of looks similar, but these two numbers are going to be way different. Okay, so the difference is not going to remain constant. Okay, whereas the ratio between two numbers is always going to be constant. So that's how you check, okay, for a geometric sequence. It's a geometric series if we add them up. Okay. The other really neat thing about this is if we have a partial sum, or if it's finite, we have a sum. So we'll say it's finite, and I'll give it an Sn, right? This will be the n terms added up. So we have a plus ar plus ar squared plus dot 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 plus ar to the n minus 1 plus ar to the n. And then I go ahead and I multiply this thing by r, right? Because there's a finite number. We're going to add them up. Okay, so we can treat them as numbers because they're sums. Okay, right? It's a sum. It's a number. There's a problem if it's an infinite sum and you don't know if it actually, what they call converges, if you don't know if it actually settles down to a particular number, then you can't add them because they're not numbers, right? If it goes off to infinity, like, you can't start adding, well, infinity and plus infinity, and that makes 2 infinity. Like, no, it doesn't work that way. So if I multiply this sum by r, right, we'll get ar. A is a common term, okay? It's like it's just a coefficient. We'll get ar. Actually, let me write it this way because we can keep the first term as the first term. So this a times r, this thing, a times r squared plus ar squared times r is r cubed, ar squared, ar squared times r is r cubed, dot dot dot, and we're going to have plus, do it right here. Okay, we're going to have a plus an ar to the n plus ar to the n plus 1. Now what we're going to do is we're going to take Sn minus r Sn. Just going to take this one minus that one. Usually, well, in calculus, usually your r's are less than 1. Okay, we like them because that's when they converge. That's when they make numbers. So if it's an infinite series and your r is bigger than 1, then you can't do this. It diverges. There's no point. Okay, but you can see, right, if we subtract, right, then this one and that one subtract out, this one and this one subtract, this one and this one subtract, all the way down, right, to this. And the only ones we have left, okay, the only ones we have left are a, right, for this one, that's Sn, minus a, r, n plus 1. So what we're going to do is we're going to say, well, let's take Sn out of here. We have 1 minus r, right? Sn is equal to a. We have 1 minus r to the n plus 1. And what we're going to do is we're just going to divide. So our partial sum, or our nth sum, is going to be a 1 minus r n plus 1 over 1 minus r. And if r is big, right, if r is greater than 1, then we get negative over negative, so that's not going to be a problem. We'll get a positive number. If r is less than 1, then we'll get, again, positive over positive, so we'll be okay. R can be negative, right? R can be... The only thing you can't do with r is r really shouldn't equal 0. Okay, because then you got 0 plus 0 plus 0, and then it's a very boring series. But if you want to add them up, that's how we end up with. Okay, and it's just a really kind of a cool way of adding up a bunch of numbers like this. Okay, so we'll go to about 10, and then I'll leave about 15. I'll leave the rest of this because the problems are a little bit longer, so I'll leave that for tomorrow. Okay. So let's see. Determine whether the sequence is geometric. If so, find the value of r. You only have like 2 series. Well, technically you have 3. You have arithmetic. You do have recursive, although it's a little bit harder to tell with recursive. And you have geometric, and then you have like miscellaneous. Okay, so there's not a whole lot you have. But let's just check. Okay, let's see. Is 24 divided by 8, right? What's that? That's 3. And what's 216 divided by 72? Right? And I don't know offhand. Okay, I suspect it's 3, but 216 divided by 72. Hey, look at that. There's 3. Okay, you could keep checking, right? But really what you want to do is just want to make sure that you've got a common ratio between all the different terms. Okay, and some of these you could do by inspection. You can kind of look at this and say, oh, wait, 72 divided by 24, that's 3. So you can check as many as you'd like, but check at least 2. All right, so this is geometric, and our r is 3. All right, let's do this. Make this smaller here. All right. So, like I said, they don't have to be, right? They don't have to be a positive number. They could be negative. So here's the idea. It's like, well, we have 8/9, right, divided by negative 8/3. Okay. And what's going to happen there is we're going to say, well, that's 8/9 times, right, 3 over negative 8. That cancels. One of those cancels, and we get 1/3. Okay, that looks promising. Let's try negative 8/27 divided by 8/9. Okay, so that's still going to be, right, that's going to be negative 8/27. We're going to have 9/8. Those cancel. 9 into 27, that goes 3 times, and that should be negative. And we still end up with negative 1/3. Okay, so every time we did this, right, it's like we're multiplying by a negative 1/3. That's how we're doing it. 8 in this case would be our a. Right? 8 would be a, and our r would be negative 1/3. And you'll note that, right, it goes positive, negative, dot, dot, dot. So it's okay that we're going to have as a negative number here. Just keep raising the power. So geometric sequence, excellent. And we have negative 1/3. to the best of my knowledge, I don't think your book lies to you too often. So I don't think in this section they're trying to trick you. I think they almost always are. Series like this. Okay, so again, see, it's going to make a liar out of me now. And we'll do 630 over 90, and we'll see what that is. Okay, so 90 over 15, let's see what we have. Okay, so we have 90 divided by 15. We have 6. And then what do we have here? We have 630 over 90. I think that's still 6. Oh, that's 7. So in this case, no, it would not be a geometric sequence. They changed this R, right? It's not the same one every time. So no, it's not. Okay, so I was wrong. They do lie to you sometimes. Good. They should lie to you once in a while. Okay. So how about this one? Let's do 27 over s squared divided by 9 over s. Okay, and let's do 81 over s cubed divided by 27 and s squared. Let's do it that way. I always have to write script s's because in the before time, students would complain and they would say, is that a 5? No, it's an s. Okay, all right, I get it. My handwriting sucks. So fine. Give you a reason to have learned cursive at one point in your life, or script, depending on what your school system called it. Okay, 27 over s squared times, and this is now s over 9. This is 81 over s cubed times s squared over 27. Well, 27 over 9, that's equal to 3. S over s squared, right? We have a canceling, and we just have an s down here. 81 over 27, that one is 3. Okay, there's 3. And then s squared over s, right? Something like that. Okay. So there we have it. Oh, I should have looked that one up. I forgot to. So Futurama. Anytime you can make a math problem and link it to Futurama is always a good day. And there's one where Bender makes 2 of himself, but there's 2 of them and they're 2/3 the size. So you get 4/3. And then everybody exclaims oh, it diverges. Yep, because your R is bigger than 1. So this series, as you go on and on and on, it will diverge and they'll have infinite number of benders. So yes, this is geometric, and our R was 3 over s, I believe. Yes, 3 over s. So I could definitely see that being a problem where the next step would be choose s so that the system, diverges or converges, and to work through it that way. Okay. So now we have A1 is equal to 17 and R is equal to -2/3. Okay. They start counting from 0 or from 1. Double check this. No, they don't bring that up until now. Okay, you have to be careful because in the calculus book, it's very important to start counting from 0, right? So it's really AR to the 0, right, at the beginning. I believe your book starts counting from 1. So we're going to find out in a minute here because I don't know. If there's an A0, then we have to figure out what the original term was. So it's going to be 17 times R was equal to, or something times R is equal to 17 is what we're going to have. Okay. So let's go ahead and assume that they count from 1 like normal people, as opposed to C programmers who count from 0. So let's go with A1 is equal to 17. A2 is equal to 17 times -2/3. So that's -34/3. Okay. A3 is going to be -34/3. times negative 2/3. Okay, so what is that? That's going to be, what, 68 positive, and that's going to be over 9. Okay, we have A4, that's equal to 68 ninths. That was positive, 1 times 2/3. Okay, so let's see, that's going to be 120, 136, I think, over 27. And then A5 is going to be, I'm not going to do this one by in my head. There's not going to be a good way to do that. Negative 2/3. And then we're going to say something clever like 136. Come on. 136 times 2 is 272 over 81. Okay. So there we go. So let's see if all that just to see whether or not 17 is the first number. Okay, 17, let's see, we have negative 34 thirds. We have 68 ninths. We have negative 136. Yep, over 27. And then finally, our last one, 272 over 81. 272 over 81. Positive, negative, positive, negative, positive. All right, let's see. Crossing our fingers. All right, they start counting from 1. So that's good to know. All right. Eventually, this bottom one will outgrow the top one. Because 3 to a power is bigger than 2 to a power. Might take it a while, but eventually this will settle down. All right. Okay, write the first 5 terms of a geometric sequence based on the information given. Okay. Oh, look at this. This is recursive. Okay. So this is AN is equal to 1/5 of the previous one. It's still geometric sequence. It's just that it's 1/5 is our common term here. It's just a different way of writing it, but that's fine. That's fine. Especially since they're having us list them out, so we can kind of take our time with it. So A1 is equal to 12. A2 is equal to 1/5 times A1. Okay, so that's 12/5. A3, right, is equal to 1/5 times 12/5. Okay, so it's equal to 12/5 here. Oh no, it isn't. It's equal to 1/5. I want to keep I'm just trying to follow their formula. That's a 1. Okay, that's 12. Don't rush. 12 25ths. Okay, A4, right, is equal to 1/5 times the previous one. So that's 12 over 125. And finally, A5, first 5 terms, is equal to 1/5, 12 over 125, and that is 12 over 625. Okay, and then so forth. Right, so very good. So let's see here. Let's shrink this down a little bit so I can look at both of them at the same time. We have 12, 12 over 5, 12 over 25, 12 over 125, and 12 over 625. Okay. Okay, beautiful. Right. Write a formula for the nth term. Okay. Again, that's pretty good. One of the ways to do this, remember at the beginning, we checked whether or not we had a geometric series. And we did that by testing out and said, well, what's the R? So we need to know what the R is in order for this to work. So let's go ahead and pick one. And they tell us, they say it is a geometric series. So once we know what the R is, we don't have to test it for multiple times. They don't lie to us like that in this book. Go to the more classes you go up, the more likely the book is going to lie to you. Let's say just the geometric series, and then you'll test it and you'll get an answer. And they'll come back and they'll say to you, haha, we lied. It wasn't a geometric series at all. You guys are terrible. All right, here's negative 16/3, right? And actually, let's go ahead and do it the other way around. Let's do, here is negative 4/3. And we're going to divide it by the previous one. So negative 16, oops. Okay, so that is, right, negative 4/3 times 3 over negative 16. This is just as an aside, right? This is just a compound fraction or a complex fraction. It's just this, right? And the first step that we do for this, there's two things you could do. You could either multiply by 3 over 3, right, and get 4 over negative 16 and get a fourth. Or, and this is the way I often remember it, but so this is like math teacher trick, but I shouldn't say trick, it's just a method that students don't remember. You do it because it is the easiest way to do this problem in intermediate algebra or in high school algebra, but chances are people don't remember it. I never did. Okay, we invert and multiply the bottom term, and all of this cancels, and then we get that, and we get 4 over 16, negative cancel, and we still get a fourth. So both of these methods are still equivalent. I think this way is just a little bit easier to follow. So since it's the same thing, I'm just writing it this way so that people will have a better idea of like what the arithmetic involved is. Okay, but but any of these methods are just fine. So use any of them. So yeah, our R, right? R is equal to 1/4. So our first term here, right? What's our A? Our A is negative 64 over 3, right? And we're just going to be multiplying this by a fourth over and over and over again. Okay. So my nth term here is A to the n is equal to, are these alternating? They are not. So I can make them all negative. So we're going to have 64 over 3. How do they want this? Times 1 over 4, 1 over, oh, geez. Let's make that negative. At this point, I'm a little worried about how they want their format. Right. So this is an A, R to the N. I kind of hope this is what they want. They did not like that. All right. Let's see here. Well, if I divide a 4 into that, I'm going to get 16 here. But to keep this consistent, I'd really want a -1 here. And they really didn't like that either. Let's try that, because I have a feeling that's what they want. Oh, no. Yeah, we used one of the 4s up. They really, what is our correct answer? Didn't I just say that? Oh, well, who knows? By the way, realize that that's going to happen. The further and further we go in this book, the more of these little holes that they're going to have for us. So, I don't know. Maybe there's a space in there or something that I didn't get, but whatever. Okay. It's aggravating. I know it's more aggravating for you guys because you're trying to get good scores on your homework, but you know, understand that sometimes like they're just not going to play. Write a formula for the nth term of the geometric series. So let's hope this one works out. Okay, so this is 5/4 negative divided by 5/3. Okay, so that's negative 5/4 times 3/5, right? Excuse me. And so it's alternating. So whatever we have as an r is going to be negative. That's okay. So those will cancel, and we'll end up with negative 3/4. If I multiply the next one by 3/4, right? That's what's going on here is we'll get 15 over, and then we can keep going with that. So that's okay. So in this case, it looks like we have 5/3. So this one is a little bit nicer because there's no common terms here. Oh, yes, there is. There's still a 3/4. Oops. To the n. All right. Now, for this one, I would really not want to combine these two because then I've got a 3 to the n minus 1, but a 4 to the n. And that's, oh, if they want it written like that, oof. Yeah. Oh, how about this? How about we take our 5/3 times 3/4 to the n, and let's go ahead and let's do this. Let's do 5/3 times 3/4 times 3/4 to the n minus 1. Okay, so I pulled one away. And that cancels, and we've got 5/4 times 3/4 to the n minus 1. Let's see if that'll work out. So 5/4. You really don't want to have like different ends. You don't want to have like an r with like, the top one is different than the bottom one. I mean, there's no rule that says you have to, you can't do it that way. But there is a rule that's going to say, good luck evaluating this thing. Okay. Because you're going to have to put it back together again in order to evaluate it. So let's see if that does it for us. Still didn't. I don't know what I'm doing with this one. They are not liking. Oh, I forgot the negative sign. Oh, how silly of me. Okay, well, we'll learn for that one. Okay. I even pointed it out. I was like, oh, it's alternating. So we're gonna need a negative. Okay, careless. Okay, so let's see here. Find the sixth term. Express the term as an integer or a simplified fraction. Okay, so we have a1, a2, a3, a4, and this is 3, and then 3r squared, 3r to the third, which is equal to 81. Well, I know that 3 to the fourth power is equal to 81. So that's what I'm guessing, is that r cubed is equal to 81/3. So r, right, is equal to, this is equal to 27, is the cube root of 27. And that's 3. So we'll say r is equal to 3. They're all the same sign, so I don't have to worry about any negatives. So it looks like r5 is going to be 3 times 3 to the fourth, and a6 is going to be 3 times 3 to the 4, 5. Okay. So 3, 4, 5. There we go. I don't know what 3 to the 5th is offhand, but it's really 3 to the 6th, isn't it? Okay, 729. see if I can turn my streak of luck around here. Something better. Okay, there we go. So let's see if the second and third terms of a geometric sequence were 16 or 64 and 16. What is the first term? Okay, so A2 is 64, A3 is 16. It looks like my R in this case, right, is a quarter. So right over, right, A1, A2. So this is, this was A1, right, times 1/4. Okay, and that is equal to 64, because that's what we have here, right? So A1 times a quarter is equal to 64, because that's how you get from 64 to 16, right? We divide this by 4. 64 divided by 4 should be 16. It's one of my favorite math jokes. Right? That's equal to a quarter. But if you do this to it, get the right answer. It only works for like 1 or 2 of these things. It does not work for everything. And if anybody's watching this, or if anybody watches this and decides that you want to show your little brother or sister how to do fractions, do not show them this. You'll screw them up for the rest of their lives. It's very dangerous. I shouldn't have showed you guys that. It's dangerous. So, but that's the case we have. So we're going to say, well, A1 is equal to 4 times 64. And I don't know what that is offhand. I think I do, but 256. Very good. Okay, so our A1 was 256 multiplied by a quarter, we get 64, multiplied by a quarter, we get 16, and then so forth. So we start off, we have 256. All right. All right. I don't know if I think I'm going to save the rest for tomorrow. Okay, because there's just a lot more of this. Right. But yeah, I'll save the rest of this till tomorrow. There might be a clever formula I missed in the book to do that, rather than the way I would normally do it. But yeah, that's we can stop there for geometric sequence. Again, these are going to be real useful in Calc 2 because we try to make almost everything into a geometric sequence because they're easy to add up because we have a formula, right? We have S is equal to 1 minus R to the n plus 1 minus R times, we know what their sum is going to be. So if we can force it into this format, we'll try, and then that way we'll be able to add them up. Okay, so that's really what you're looking for in the end here is what is going to be the geometric sequence. Unfortunately, you have to wait like a whole 2 semesters to get to the punchline, but there we are. Okay, so I'm going to go ahead and stop talking. I will post this one, and we'll go from there. Okay, so thank you, and I'm going to stop.